I think we are at week number 5 at the moment. So what I will do first, I will take you through the key points or the key concept. I'll just give you an idea what week number 5 what we have done up to week number 5, and after that I will answer some of the queries that I have already received, and I also will let you know what what kind of textbooks actually you can consult, because I think this is the one thing that I have not talked about in my lecture classes. So first of all, you see, this quantum optics already you must be having some fair bit of idea what it is. It basically combines the principles of quantum mechanics and electromagnetism, and in essence quantum optics studies the interaction of light with matter, quantized matter, that is the semi-classical approach. And also mainly in quantum optics what is done is that you consider the quantum aspect of the radiation and the quantum aspect of the matter, and then you study the combined effect. And you have already, so let me, okay, right, in week 1 we have focused on this two level atom, and there we have learned how to write down the Hamiltonian of a two level system. These are the snapshots that I have taken from the lecture notes, and I hope you are getting the lecture notes as well, the PDF copy of the lecture notes. And there we learned that when we are having an isolated two level system, we can write the Hamiltonian in a very elegant form using this Pauli matrix, sigma, epsilon dot sigma. This we have learned. And then some basic tools of quantum mechanics that we need in the course also was addressed in like week 1. One of the main uh, thing that we have learned in week 1 is that how we can express the Hamiltonian in the matrix form using some basis state. And then we have heavily exploited this particular the condition called the completeness condition. K type bra I sum over all of them is going to be identity operator. This we learned there. And in fact towards later on also, as you will see in week 7 and 8, we are actually exploiting this particular completeness condition uh, in many of the problems that we are discussing. So these are the basics that we discussed in week 1, and then we also saw the how the geometrical representation of quantum states in the context of a two-level atom can be done. And we saw that every point on the sphere, what is this called, this block sphere, represents a quantum state, and we can write it as a superposition of K0 and K1, and this we learned in our week 1. And in the second week we started discussing how the atom is interacting with a classical light, and that was the semi-classical approach. Here the electric field of the laser radiation is taken to be linearly polarized, and it has amplitude E0 with frequency omega. And then it's not necessary that the frequency of the laser radiation exactly matches the energy difference between the two energy levels. There we saw that this can be slightly detuned, and this detuning parameter is of significance, quite significance, that also we learn later on. And by manipulating this detuning parameter we can achieve a lot of application can be done. One most important concept of quantum optics that we have learned is the rotating wave approximation. There we basically we saw that how we can and why we can neglect or discard all the highly oscillating term. because if we are having very highly oscillating term, then the time average, the time window in which we are making the measurement or calculating the expectation value of a quantity, because this is so highly oscillating, the time average, if you take it, then it go to zero. That's the reason why terms like mu plus dot e plus or mu minus e minus is not going to contribute, and these terms can be neglected, and that simplify our mathematical analysis a lot, and that is what is called a rotating wave approximation is. And we wrote down the Hamiltonian for the two-level atom using this rotating wave approximation, where this omega is the Rabi frequency. Here we learned that you see we have this explicit time dependence is appearing, e to the power I omega t and e to the power minus I omega t here. And to get rid of this explicit time dependency, we can go over to a new frame of reference by making unitary transformation, and thereby we saw how we can get rid of this time dependency part, and it's a very effective tool. And this tool we have utilized particularly in when we have done applications of quantum optics, particularly in week 7 and week 8, which is yet to come. You will see that we are actually using these tools very judiciously there, and that simplifies lot of things there, and physics comes out very nicely. I admit that this course is bit mathematical in nature, but it is needed, because that's why the course name is Essentials of Quantum Optics. You must have to go through this all the essential mathematical steps, then only you can take up an advanced course and you can understand the nitty-gritty of many experiments. So that's how this course is designed, and we cannot avoid this mathematical calculation. You must have to learn this all these necessary tools. Anyway, so this Hamiltonian, transform Hamiltonian, when we are having, as you can see, then this explicit time dependency is no longer there. And we discussed the so-called Rabi oscillation, one very important phenomena in quantum optics. This actually appears even in the domain of when we consider quantized radiation and quantized matter. At this stage in week 2 here, we are considering the matter to be quantized, but the radiation as classical. Even in the semi-classical domain, as you can see, just by manipulating this Rabi frequency, you can take the atom from the ground state to the excited state and so on. Or you can even create, if you omega t is equal to, say, this capital omega is the Rabi frequency, t is the time. If the product is such that it is equal to, say, pi by 2, then you will be able to create a superposition of the ground state and the excited state. And that way you can manipulate a two-level system just by applying the appropriate Rabi frequency or the waiting for the appropriate measurement time, doing the measurement time judiciously. Okay, ultimately the product capital omega t matters. So next we have discussed about the dress state, because why it is called dress state, basically as if the atom is getting dressed by the incident laser radiation, and then this kg and kt, which were generally the eigenstate of an isolated atom, they are no longer eigenstate of the system, but the eigenstate is now becoming kate plus and kate minus, and we showed that we can write any arbitrary state, as you know, we can write it as superposition of eigenstate, and that's what we have done here. Kate plus is written as a superposition of kg and kt, and similarly for kate minus, and kate plus and kate minus are called the dress state, and these two dress states has to be orthogonal, and of course this has to be normalized also. That's why this coefficient sine theta cos theta is there, and by calculation we saw that this angle called the Stackelberg angle tan 2 theta is equal to minus capital omega by delta. All these things we learned in week 2, and then main result, important thing is that when this coupling is there, capital omega is basically it's coming because of the coupling of the atom with the radiation. because of this coupling, you see this energy level no longer cross each other. Rather, what happened is that this crossing is getting avoided. And this is a typical feature of any system, quantum optical system. Whenever there is coupling, you always see this avoided crossing phenomena. Then in week 3, we went on to discuss the so-called density matrix formalism, because you see, generally when you are having a system which is isolated, then you can represent the state of the system by state vector. But when the system specify the state of the system, state vector of the system, there you have to use the density matrix, and this density matrix formalism we discussed. And for example, here you see this density matrix 2 by 2 matrix that we have written here. It's for a 2-level atom, and it is important to understand the physical meaning of all the elements here. Rho 1 is the population of the state 1, rho 2 is the population of state 2, rho 1, 2 and rho 2 are the coherence of the states. Whenever rho 1, 2 and rho 2, 1 are non-zero, that means you can create there is basically coupling between the energy levels. That's how you can think about it. And these are coherence terms. And we also can find out what is a pure state and what is a mixed state just by calculating rho square, taking the trace of rho square. Then if it is equal to 1, it's a pure state. If it is less than 1, that's a mixed state. We also learned that you can calculate the expectation value of an operator very easily just by calculating the trace of the product of the density matrix with the operator. And this density matrix evolution equation is given by this Schrödinger von Neumann equation. This also we discussed in week 2. Then we also discussed about optical block equation. All right, so then composite system is something that we discussed, where how we can discuss the physics of a two system A and B rather than a single system. So that can be done by invoking the tensor product or the direct product. So system A lives in the Hilbert space HA and B in Hilbert space HP, and the overall Hilbert space for the system A and B would be the direct product of the Hilbert space of A and B. These things we discussed with by taking out some example also we discussed in the class. And then one important concept that we discuss is the reduced density matrix. The idea behind the reduced density matrix was that sometimes you are not interested in the both the two systems, rather you are interested only on one system. For example, if you have a system and it is interacting with the surrounding, you may not bother at all about the surrounding. So in that case, you need to have the information exclusively about the system, and that you can do by tracing out the surrounding. And for example, you can find out the density matrix of the system A by tracing out system B, and we discuss it by some example also how that can be done. And it's a very effective tool and very much used in discussion of quantum entanglement and so on. I hope you have understood this concept. I have discussed it via couple of examples, not only in the lecture class, also in the problem solving session. And I urge all of you to take the problem solving session as a part of your lecture only, because many assignments and later on also exam is going to be based on that. And exam is going to be, by the way, very simple. Let me tell you this. Your main exam is not, though I have put up everything in the lecture classes, I have given you all the detailed calculations so that you learn it, but many things are so detailed that is not that everything is going to be asked in the exam. You just have to do the assignments properly and then the problem solving session carefully, and that should be sufficient for it. So exam is, I promise that that's going to be very easy affair. Anyway, so now next in week 4, we discuss about quantum computation. We have started with only some basic concepts I discussed because I thought that one of the important application of quantum computation is quantum optics. Basically, quantum optics knowledge is required to do research in quantum computation and quantum information. I have just given you a bit of glimpse, though it is not a detailed course on quantum computing or quantum information. So there we learn what is a quantum bit. Quantum bit is again nothing, it's but a two-level system, superposition of ground state and the excited state, or upspin state or the downspin state, and so on. So all you have learned already. And in quantum computation, this block sphere formalism becomes quite useful. And by manipulation of quantum qubits, generally in terms of block sphere, we mean that you just take one state on the surface of the block sphere from one point to another point, and that you can do by that Rabi oscillation technique that we have learned, that can be utilized to take the state from, for example, you can take the state from K0 to K1, or from say at any point. You can do it by appropriately choosing the product of the Rabi frequency and the measurement time. So next we discuss about the 2-qubit system also, and 2-qubit system can also be, if you have say only 2-qubit, then you can write it as a superposition of this. Only thing is all these coefficients should go to equal to 1, and by convention when you are writing K00 or K01, the first element always represents the first qubit and the second one represents the second qubit. Okay, for example, here if you are having 0 1 0 1 0 means the first qubit, that means the first qubit in the K0 state, and the second qubit is in the K1 state. And similarly for 1 0, that means the first qubit is in K1 and second qubit is in K0 state. So then after that I have discussed about some quantum gates. It has some classical analogies there. In the case of quantum gates, states are anyway represented by K1, K0, and so on. And if you apply this sigma x matrix, the x component of the Pauli matrix, you can take the state 1 to K0 and state 0 to K1. So that's how a quantum NOT gate is represented, mathematically speaking. And we have discussed about the Hadamard gate. Don't get confused with the Hamiltonian. This is simply Hadamard. This Hadamard gate operation is that when you operate this Hadamard gate on K0, it creates a superposition of K0 and K1, and that is basically a K plus state. Also it is called a diagonal basis, will be represented by K plus and K minus. And H1, if you apply, then you resulted in the antisymmetric superposition of K0 and K1. Now, if you look at the block sphere, Hadamard gate operation is basically doing what? For example, suppose you are in K0 state, that means in the south pole, applying the Hadamard gate, you are going over to the point M on the block sphere, right? That is what it is done. And this is what we are saying mathematically speaking. But physically speaking, in the laboratory, then the technique is again you apply the appropriate Rabi frequency and also observe it for the appropriate measurement time. That is one of the technique by which you can take the state from K0 to from the point S to point M and so on. Okay, that's the way. So Hadamard gate is very useful. It's a single qubit gate. Then we went on to discuss C-node gate, which is of extreme importance. C-node gate, this principle is this, that when you are having basically these two lines, you see the first line refers to the first qubit, second one refers to the second qubit. When the first qubit is the control and the second qubit is the target, and the principle is that when the control is 0, you do nothing, target would remain as it is. But if the control is 1, then the target gets flipped. Okay, that's the principle. So here you have seen when the control is 1 and your target is 0, the target gets flipped, then 1 0 becomes 1 1. And similarly for 1 1, if the target is control is 1 and target is 1, so target get flipped because the control is 1. So this is a simple principle on which this C-node gate operation is done. Then we briefly discuss about quantum entanglement, some measures we discussed, and we can find out how you can ascertain, mathematically speaking, that two systems A and B are entangled. You have to just to calculate, the rho square for system A and system B, and if you find that rho square is less than 1, that means system B, when you have taken the reduced density matrix and found that rho B, and then calculate rho B square and take the trace, if less than 1, that means the system B is in a mixed state, and that means the system B is entangled with system A. Similar is the case with system A as well. If trace rho A square is less than 1, then A is entangled with B. And if it is the pure state, then of course they are not entangled. Pure state, that means that you can always write it as the system A and system B state can be written as a product state of A and B. Okay, so this we discussed. And another method we discussed is this von Neumann entropy technique. We can calculate what is this von Neumann entropy, and thereby also if the von Neumann entropy, respective von Neumann entropy for system A and system B turns out to be non-zero, that means there is entropy is non-zero, then in that case also we can find out that A and B are entangled. Okay, next we discuss the no cloning theorem, and then we discuss about the quantum teleportation. Everything we have done it in somewhat details. No cloning theorem, I have also given you the proof. Then in week 5, which is currently going on, we have discussed this open quantum system, and this particular week is little bit, I have deliberately done all the maths here because it is important to learn how this quantum master equation, which is said to be the powerhouse of quantum optics, is basically derived. And by open quantum system, we mean how our system is getting coupled to the external system, which generally we cannot directly track. And then we basically have this, the environment or the surrounding is called the reservoir, and Hs represents the Hamiltonian for the system, and Hsr is the interaction between the system and the reservoir. And we want to work out a density matrix for the system reservoir. This combined, this is going to be given by this Schrodinger von Neumann equation by applying various detailed mathematics I have done in the class. Ultimately, what we got is that how this system density matrix evolves in time. Time evolution is given by this particular equation, and this has a peculiar form. This is called the Lindblad super operator, and this operator ensures that your the density matrix remain Hermitian, and its unitarity and other things are getting maintained. And and we have actually done some example. That is what is more important. If you are finding this particular week little bit difficult, I would say कि you just focus on how this particular density matrix equation, Lindblad master equation, we have applied it for two-level system with an harmonic oscillator at 0 temperature and finite temperature. Just focus on that. You can forget about the detailed derivation part. You can anyway go through the derivation and everything, but as regards examination is concerned, this particular part is, as I think I have mentioned that in the lecture class as well, that is, I'm not going to ask you any mathematics there, but it is important how to know how this Lindblad master equation is applied for simple, say, two-level system or a harmonic oscillator and so on. I have given you example. I have done the calculation in great detail there. Please practice that, and that should be good enough for you. Next, we discussed in this week 5 electromagnetically induced transparency. Here also I have given you the detailed discussion, but you have to focus on only the main concept here. What it basically means that when you are applying a probe field and a strong pump field, then generally what happens, the probe field get absorbed if there is no strong pump field, and this particular phenomena is so peculiar that in the presence of a strong pump field, the probe field can pass through the medium without getting absorbed, right? That means it can get transmitted, and this is why it is called electromagnetically induced transparency, and this induction of the transparency is done by the presence of the strong pump. We discussed the physics here, and this point has to be kept in mind, that the probe is basically getting transparent. Okay, it can pass through the medium without getting absorbed, not the pump. Okay, probe is in the presence of the pump, this probe is passing through the medium without getting absorbed at all. Then we discussed some requirement. This is, you have to understand, because all the detailed mathematics that we have done, the main result is that the decoherence rate has to be very small if you really want to have realization of EIT in a laboratory. And this decoherence rate gamma 1 2 has to be very small, and also EIT arises due to the coupling between the first rho 1 3, and who is basically rho 1 3 is what? It is corresponding to the energy level 3 and 1, between which you are applying the probe field. Okay, this has to be, it is arises due to the finiteness of rho 1 3, so it has to be a finite quantity. And also we discussed one simple interpretation of EIT, that is because of the quantum interference effect. Now what is happening here is that you have two paths. You see, ultimately you don't want that your probe is getting absorbed. That means this it is going to get absorbed if the atom is going from the state 1 to state 3. If you can somehow cut off this channel, then this probe can go through the medium without getting absorbed, right? So how this is done, there are two parts. You can go to this energy level 3 from this ground state 1 via two parts. One is that directly you can go from 1 to 3, and the another one is this, because you cannot go from 1 to 2 directly. This is dipole forbidden, as we have discussed in the class. So another path is that you can go from 1 to 3, then 3 to 2, and then 2 to 3. Now these two paths, when they interfere destructively, then you will be able to cut off this transition, and that means this probe can pass through the medium without getting absorbed. So this is basically the essence of what is called EIT. Now let me talk about textbooks. So basic textbook that I have consulted primarily, for example, in week 6 in particular, I have used this textbook, Quantum Optics by Mark Fox. And for quantization of radiation and these things, you can consult this book on Introductory Quantum Optics by Gary and Knight. These books are very simple, they're written in a very simple language, all of you can follow. And I don't think Indian edition of these books are also not very costly, you can buy that. And then some advanced book also you can consult. For example, in week 7, week 8, I have made things very simple for you. I have given you all the steps, as you will see in week 7, where we are discussing circuit quantum electrodynamics, and week 8 we are discussing, and you are definitely going to enjoy week 7 and week 8 because it is heavily loaded with application, and that too what is going on currently, what is going on in the research area. Okay, so this Perry Mester book on quantum optics is very nice one, and then Quantum Optics by Milburn, Walsh and Milburn is also good, where you can discuss, they have discussed about this quantum master equation and other things, both the books, so you can consult them as well. But what I would say, that you follow my lecture notes and follow my lectures properly, and whenever you attend my lectures, you just attend it with a piece of notebook and a pen, right, and then work on it. Things are not, I have given everything in great details, and so hopefully we'll learn. Now finally, let me come to some queries. Some people ask me, please send us study materials in PDF to download. As far as I know, lecture notes are provided in PDF form. If it is not, I will still consult with my TA and I will inquire whether they are sending the study material, the lecture notes or not. But I will make ensure that this is given to you every week. You should get the study material in PDF. Hopefully you will be able to download. And another query was, could you please send PDF of reference books? Unfortunately, I will not be able to do that because that would be violation of copyright, and some of the materials, of course, you can get in online also. So yes, this is, I am unable to do this. I cannot send you PDF of reference books. And one question was, I live in USA, but how can I get certificate if I finish this course? I think you have to appear for the examination, and then if you clear it, then they will send you the certificate. I'm not very sure about it. Maybe you should contact NPL team. They will be able to answer this query. Okay, then another question was lot of questions are there in this gentleman's query. He was asking, he's asking, can you explain about quantum optics with cryptography other than QKD application? Okay, to answer this particular question, let me tell you, this course is not about cryptography or quantum information and so on, but I will provide you some reference there. Maybe you will find the answer there. And can I able to design a quantum photonic chip for communication device through simulation, and what is the procedure? For that, I will give you the answer to this question also later on. And then you are asking, in this course, mathematical concepts are there, needed a book for study to solve these problems and advanced problems. Is there any opportunity provided for research scholar? Okay, regarding this book for study to solve these problems, as I have already told you, shown you these books here a lot of examples are there. Worked out examples are there, and at the end of each chapter, problems are there. You can practice those problems, and at the back of the these things, they have given you the solution also. Basically the answers they have given, so you can try to do the practice there. And I will give you some other reference also, particularly for quantum information purposes, for which I think this particular is very much interested in quantum cryptography and so on. Is again, his another question is there any opportunity provided for research scholar to visiting IIT Photonics lab? Actually, once this course is over, whoever is doing good, maybe they can get an opportunity for internship, and NPTEL arranges these things. So if I ask for internship, I think I will ask for one. So then you can apply through that, then you may actually come and get involved in the kind of research we do. Let me tell you honestly that I am a theoretician, but in our IIT Guwahati, we have some experimentalists are also there, and we collaborate. And particularly, I collaborate with experimentalists from outside, for example, ISC Bangalore and so on. So my research is basically, so though not experimentalist I am, but theory part is what I contribute, and that's why I have a very strong inclination to experiment. And simulation and other things. For that, you can nowadays, there are many tools are there. I will show you some. Then you are asking what are the expectations needed in this. Generally in our lab, if you want to work in our group, if you have done this course successfully, then you are eligible. That's what I would say, because all the basics, whatever is needed, is taught in this course, and that is good enough to pursue any higher or advanced level course. And let me mind you again, this is essentials of quantum optics. This is definitely needed whenever you want to go to do research in any other areas where quantum optics is required. Okay, these are the books that I would like to mention in particular to your query. You can look at this book on, I think maybe already you know this Nielsen and Swang book on quantum computation and quantum information. If you have done this course, then this book would be pretty easier for you. Then these problems and solution in quantum computing and quantum information. There are a lot of solved problems are there from quantum optics as well, and they are targeting primarily on quantum computing and quantum right. And finally, this quantum computing book by this Nakahara's and Omi book is very good. You can also consult this book. I think with this, let me end my presentation. And okay, so this I forgot to tell you. Some software you are asking, some tools for simulation. You can learn about Qiskit, and then Qiskit is freely available, and you can do a lot of simulation using Qiskit. And this one question you asked about simulating quantum photonic chip. When I inquired about this query, I found that there is already a company is there, and you can basically use their tools to simulate quantum photonic chip. They have come up with some tool called Photon Force. You can utilize that. Okay, so I think with this, let me stop my presentation. And if you have any further queries, whoever is present, I'll be happy to take. Let me once again tell you about the examination particularly. Please take the examination and don't worry about that because the course seems to be mathematical or whatever. Examination is going to be simple. As you have already seen, all the assignments that I am providing you are not very difficult. So your final exam is also going to be of that type only, very simple in nature, and only the whatever essential is required that is going to be asked there, and you can very easily pass the exam also. And in fact, you can do very good if you follow the main things properly and do the assignments regularly and follow the problem solving session and so on. So I request you, please give the exam, don't skip it.
Hello, sir. I have one question.
Yes.
I have posted it in the chat. I asked it. So during your lecture, in one case, you have named the south pole of the Lord sphere as the ground state, whereas in a different occasion, you have named it as the excited state.
Okay. All right. Oh, I get it. Actually, you see, it's a matter of convention only. Sometimes what may happen is that people may take 1, 0 as that column vector as the ground state and 0, 1 as the excited state, or vice versa. It's a matter of convention. Only thing is that once you, for a certain set of calculation, if you have taken the south pole as your ground state and north pole as your excited state, or north pole as your ground state and south pole as your excited state, you just stick to that convention throughout the calculation. In between, don't change it. Then you will not end up in any trouble, and everything will be physics wise, nothing is going to change. You will be correct. It's a matter of convention only. In some textbook, you will find that they are taking the ground state as the excited, south pole is the excited state and the north pole is the ground state, or vice versa.
Okay, thank you.
Yeah. Yeah. Anything more?
Hello, sir.
Yes.
Sir, I wanted to ask about the exam. It will it be in MCQ form or subjective type, objective type or subjective type questions?
No, it is going to be objective type.
Okay, okay, sir.
Yeah, it's objective type. The exam would be, you need not have to worry at all. That's what I am saying. Exam would be easy. Only thing is that this week 7 and week 8, that is going to be on the bit higher, but you will enjoy that because that is very important. You will see. That is what is going on currently, as I said, whatever is happening in the research arena, for example, in the domain of quantum technology and our India's this national quantum mission and so on. So I have tried to cover lot of things there, but with detailed calculation and detailed explanation. And if you go through that, I think pain, and then you will really enjoy and you will learn something. That much I know. And these are some materials that you will not get in conventional textbooks as well, at least in quantum optics textbook. So that week 7, week 8, and week 6 is all about quantum method of light and radiation, which is heavily inspired by some chapters in Mark Fox, that quantum optics book. But I have made the thing simple there also. So you will love that week also, week 7, week 8, a lot of materials I've covered. So those are easy materials, but I have done it in somewhat details. Yes.
Sir?
Yes, yes.
I already done your quantum entanglement and fundamental measures NPTEL, sir.
Okay,
And
okay.
this essential for quantum optics also very interesting to do the mathematical calculation and other stuffs too. The previous lectures continuation is there in this lecture also,
Right.
sir. If I'm working on quantum cryptography means in stimulation based I'm working, sir, in that domain purely.
Right,
I
right.
want to pursue my postdoc in experimental domain like quantum optics means. What can I do in my pre-postdoc research, sir, in that?
You have already completed your PhD, right?
No, sir. Next year I'm going to complete, sir.
Okay, all right. Oh, that means you just want to say that how you can prepare yourself for doing advanced these things, right? That's what you were
Yes, sir.
asking.
I want to pursue on quantum optics or any other field
Right,
related to
right.
your field.
Okay,
Yes.
okay, good question. So one
Yes.
thing, did you actually, I answered your certain queries. Were you there? Because I cannot see who are present and who are not. I
Yes, sir.
just talked about this.
Yes,
You
sir.
get okay.
Quizkit, I'm working on Quizkit only, sir. Stimulation based work, all
Okay,
doing in Quizkit only.
right. Then there is another tool that is called Qtip, that is Quantum Optics Toolbox, that is Python based. That also
Qtip.
you should learn. Okay, Qtip. So,
Okay, sir.
right. So let me write here. You should also
Qtip.
learn
Yes, sir.
about Qtip. So
Sir,
there are lot
only
of
one
people.
doubt, sir.
Yeah, there you
Strawberry
can.
fields also there, sir. Strawberry, Xanadu based strawberry fields.
Yeah, that is there, but generally for our quantum optics purposes, what we have found is that this QTIP is pretty good. It's a quantum optics toolbox, and yeah, nowadays there are many other platforms are there, but QTIP is open source, and uh, we generally in our group we use QTIP quite heavily for all kinds of lot of things we do. there, so that you can do. And I would say that if you really want to go to quantum information, this particular book by Nielsen and Swang, you should give it a thorough read. This is going to help you.
In research point of view, I'm asking, sir. For example,
Uh-huh.
before
And
we need to
then,
go for any lab or
right.
anything,
And
we
at
need
the
to.
moment, yeah, research point of view, uh, generally you can always learn the research tools by working out some classic paper, for example. Okay, maybe you can just go through what's going on in the current research sector. Physical review letter journal, you can look at it. Physical review A, which is primarily for quantum information and quantum computing and quantum optics. We generally publish our research articles there. You can go through the articles there, and you can walk through some review articles. And visiting a experimental lab at this stage, I don't think that is required, because ultimately you would like to enter into a PhD program. And to enter into a PhD program, first of all, you have to clear the PhD entrance examination. Particularly, you have to face through interview and all these things. So strengthening your basics is definitely going to help you. And I'm sure this particular course, if you have done it, then generally in interviews, people are going to ask you basic concepts only.
Sir, I'm
So,
asking postdoc opportunity, sir, not the PhD, sir.
oh, you have, okay, I would say you
I'm
go slow,
currently.
because first you do PhD, na? Then after that
Uh,
you think about postdoc. So you are
uh,
asking postdoc is dependent on your the kind of topic you are going to choose, that's going to decide your postdoc. And if you are choosing a very, the area depends a lot regarding postdoc is concerned. What we have seen is that just by doing a PhD, you may not get a postdoc position, because certain areas are there at the moment where a lot of funding is there. For example, generally in quantum optics, postdoc is easily available, because the area is pretty trendy and pretty hot. And so for preparation of postdoc, I don't think this is the right moment to think about that. I would
yes.
request you to go step by step. And once you complete your postdoc, PhD, and to get a good postdoc, you have to get, a couple of good publication in journals like Physical Review or Physical Review Letter, or even other journals. But if you can get publication there, you will get postdoc. And then you decide your postdoc. You have to search for some groups where, whatever tools that you have learned, you can apply those tools in your that group, to who is actually you want to go. So I would say, at the moment, if you have done a PhD, then I could have said certain things a little bit more differently. Okay, but you are yet to complete your PhD. So later on, maybe you can drop me an email when you complete your PhD. At that moment, maybe I'll be able to answer certain queries more clearly after looking at your profile. Okay.
Thank you so much for your
Oh,
answer, sir.
yeah, yeah.
Thank you,
All
sir.
the best. Yeah.
Thank you, sir.
So, is there any other queries? Uh, if not, maybe,
Hello, sir.
yeah.
I wanted to I wanted to say that in NPTEL I have enrolled in one more course, and there a teacher comes, means like every week there is a live interactive session of problem solving. So that helps a lot for me. Means that is very helpful. So can we have live sessions here also in this course every
Uh,
week?
every week is not possible. The reason being is that we have other, teaching assignments are there. I have to take my semester courses, and I'm heavily busy. But I have tried my best by offering you problem solving session. As you can see there, if you follow this problem solving session, and now I have given you some these books also, maybe that you can consult. And another thing is that we are going to have another live session. So if you have any query, anything, then you can let me know beforehand, then maybe if that helps.
Yes, sir. Yeah. But actually, in that course, the teacher who teaches us the lecture or video lectures, that teacher does not come in live session. Live session, means the teacher who comes in live session is a PhD scholar, and I can means like I sometimes ask him about career options and all, and the weekly
Okay,
interaction helps
okay.
a lot.
Right. Okay, you can do one thing, I think. Uh, you can ask whatever your query you are having. Suppose some query you are having regarding some concept and so on. Then in our that web page where you access these materials, there you can ask the queries. Then we'll try to answer that. Is that going to help you?
Yeah, yes, sir. Okay.
Yeah, periodically you do that, and whenever we get time, we'll get back to you and we'll try to answer your queries. That much we can
O-
do. My TA will do
okay,
that.
sir.
Okay. Yeah. Anything else? Okay, then I think should we sign off, Rekhaji? Yeah. Should we wait for some more queries, or should we? Because it appears that I did not see any queries in the YouTube chat as well. Um, so maybe they will ask more questions in session 2. Okay. So should we sign off now then? Okay. 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 Thank you everyone, and thank you so much for attending. And it's lively having a discussion with all of you. Thank you so much.
Thank you, sir. Thank you very much.
Thank you, sir.
Yeah. All the best. Bye.